So the last thing before we move on to the next one is this idea of the chemical dance. A lot of times we use analogies to represent these patterns that we're seeing. And one analogy that we use a lot of times when we're talking about reaction types is this idea of the chemical dance or the chemical prom. So a synthesis reaction would be sort of like two people that came to the prom alone. They met at the prom and they ended up spending, the rest of the dance together. They had a good time. Who knows what happens after the dance. Maybe they go on a couple dates or whatever. But they started off separate. Now they're together. All right? Next, once again, because you know English, you probably could guess what's going to happen here. Decomposition reaction. A reactant compound is broken down into two or more simpler substances. Okay? So we're taking things that are complex, like a finished puzzle, and tearing it down into the pieces that made it up. It doesn't necessarily have to break it all the way down to elements, but we're taking something big and making it into something small. In your can of pop or Sprite or fizzy, whatever it is, okay? General form. We start off with these two things together, and we end up with them apart, right? A-B compound, a compound containing A and B, ends up product-wise as A plus B, as two separate components. The first example here is what goes on when you open up a can of pop. Pop is made of something called carbonic acid, which is H2CO3. Okay? Some of you are probably familiar with the idea that if you stick a nail or something metal in Coke, after a while, it starts eating the nail away. Yes, it's acid. It's not burn your face off acid, but it is acidic. But this is a certain type of acid that when you open it and you change the pressure that that acid is under, it actually breaks down into H2O plus CO2. What happens when you open a can of pop or a bottle of pop? Bubbles. Guess what those bubbles are? CO2, carbon dioxide. Okay? Eventually, if all of this carbonic acid breaks down and you lose all of the CO2 to bubbles, you end up with just water. You know what you call that? Flat pop. That's what it is. Okay? The second example is something that we refer to as electrolysis. This won't happen spontaneously. Water doesn't break down into hydrogen and oxygen. But if you pass a strong voltage through some water, it will break down into hydrogen gas and oxygen gas. And if you look at the ratios, you'll actually end up with twice as much hydrogen gas as you do oxygen gas, making connections back to those balancing equation things that we were doing and what the subscripts actually meant. If you talk about the chemical dance or the chemical prom, this is kind of an ugly one. Two people go to the prom together, but they end up not together. That gets kind of ugly, right? So watch out for that one. Next, single replacement reaction. Single replacement reaction has a real distinct form. Definition: one element replaces another element in a compound. As far as our general form, it looks like this. A plus BC for reactants, so we're starting off with an element and a compound, and we're ending up with an element and a compound. Basically, an element, a free element, is going into an already formed compound and kicking one of the parts of that compound out, and then forming its own compound with something that already was joined to a chemical bond, right? Once again, if you think about this energy process, right? Which one's going to have the lower energy? If A bonded with C, like it is here, has a lower energy, then it's going to happen. If B bonded with C has a lower energy, then this reaction isn't going to happen. Okay? But, more importantly, single replacement reaction is a real easy one to identify. It's always element plus compound gives you element plus compound. This picture here, this sequence of 4 test tubes, actually is representing that this reaction that I have here. The clear solution is a solution of silver nitrate. This wire is a copper wire. When the copper comes in contact with the silver nitrate solution, AgNO3, copper bonded with nitrate is lower energy than silver bonded with nitrate. So we end up with the copper going in, kicking the silver out, and forming its own compound with nitrate, and leaving silver out there hanging just by itself. All of this little mossy fuzziness that's showing up along the edge of the copper wire is actually silver that is being displaced from that compound that it had originally formed with nitrate, and now it's just out there on its own. It can also happen to anions too. Chlorine plus a potassium iodide. Chlorine's a nonmetal. It forms an anion. It's going to go in and it's going to replace something in this compound, but it's not going to replace potassium. It's going to replace the iodine. Why? They're both nonmetals. They're both halogens. They behave similarly. So it goes in, chlorine goes in, kicks the iodine out. It forms its own compound with potassium, right? And then it leaves iodine out there by itself as an element. Yes, it's a diatomic element, but it's still element plus compound gives us element plus compound. Yeah. As far as the dance example goes here, this is a little devious, right? Somebody comes to the dance by themselves, and two people come to the dance as a couple, but that someone who came by himself ends up kicking one of the partners out of this couple, forming their own partner, leaving poor B all by itself. That's a devious one. That's not a nice thing to do. So if you find yourself in that situation, don't do it. I know it's a chemical reaction, right? But control yourselves. All right. Last type of reaction we refer to as a double replacement reaction. Whereas before we had a single replacement, one element goes in and kicks out another element from a compound, here we start getting a little more complex. It basically looks like we're changing places. Okay? Two elements in different compounds exchange places. So you see here in the picture, right, you got two black circles that are joined together in a compound, two white circles joined together in a compound. They switch, one black, one white. General form, AB plus CD is equal to AD plus CB. Notice, if A is the cation or the metal in this ionic compound here, it's going to be the cation or the metal in this ionic compound. Cations replace cations, and anions replace anions. So D and B are going to switch places. A and C are going to switch places, but A won't switch places with D. You won't find AC plus BD. Why? A and C are both cations. They're both metals. They won't form a compound with one another. But you trade fronts and backs, basically. Right? So for this one, you're looking at two compounds, right? Potassium iodide, ionic compound, lead nitrate, another ionic compound. The potassium goes in and changes places with lead. So now it forms a compound with the nitrate, potassium nitrate. The lead trades places with the potassium, and it forms a compound with iodine, lead iodide. This is actually, if we go back to this picture, right? This reaction is that potassium iodide with lead nitrate solutions. They're both clear to begin with, but once you mix them together, you make the lead iodide, which has this really bright purple color, and you'll get to see that in lab on Thursday. Okay? So double replacement, compound plus compound equals compound plus compound, where the fronts and the backs are switched. Okay? There's a couple of examples. Chemical dance, this is kind of a weird one, right? Two couples show up at the dance together, right? Two couples show up, well, you know, each of them being a couple, and they go home with each other's dates. So that's kind of a weird one, a little scandalous, and probably would be talked about over Facebook, I would imagine. Summing it all up, there's your star. There's your 5 different types of reactions. Remember we said all reactions are going to result in something being formed that has different properties than we started with. But we see that patterns develop, that we see certain things happening over and over again. Combustion, where oxygen is one of the reactants. Synthesis, where we're taking simple things and putting them together and making them into more complex ones. decomposition, where we're starting with complex things and breaking them down into simpler things. Single displacement or single replacement, depending on what book you read, it really doesn't matter. One atom goes and kicks something out of a compound that's already there. Why? Lower energy. If it has lower energy bonded to the part of that compound than the original compound had, it'll happen. Then double replacement or double displacement, where we're ending up with two things that are sort of switching places as we go along. Okay? So there's your reaction types, there's your star. Fill it in with as many examples as you want. Okay? Hopefully you were doing some things as we went along. If you take a look at the calendar, and let's go back to more recent times, because I went back there. Here, Tuesday the 17th. We took the quiz, went over types of chemical reactions. That PowerPoint is available for you if you want it. Right here underneath it'll say class recording part 1, part 2, so you can listen to this again if you really, really want to. Then, short little reading assignment, a couple of pages from your book, a couple of problems from the end of section 6.2, and then the end of chapter 6, reinforcing these ideas of types of chemical reactions. I will see you on Thursday for our last block day of the year, and our lab dealing with these different types of chemical reactions. Have a good day, everybody. See you on Thursday.